Algebras. Welcome to your Chapter 12, Lesson 3 notes. We're going to look at exponential growth and decay for 2 days. So this is day 1 of 2 days worth of talking about how our functions will increase rapidly or decrease rapidly. We're actually going to have a nice little equation we use and plug into by the end of the lesson. So we'll start applying that and what we know about it as we kind of go through this. Okay. So we're going to start with this question that I always ask. And it's kind of neat to then look at what this will be. But would you work for a penny if that pay got doubled every day? So would you work where the day 1 is a penny and the day 2 is 2 cents and the day 3 is, well, this is a little backwards from what I'm saying. That day 1, you get 2 cents. Day 2, you get 4. Day 3, you get 8. So day 4, you're at 16 cents. Now this is all in cents, right? This is all in cents. So I'll convert it in dollars below. But then 32 cents, double that, 64 cents, right? Double that, just so you know where I'm coming from here. 64 times 2. Okay, $1.28, day 7. I need to get to day 10, so let's keep multiplying. 128 is day 7, times 2 is day 8, times 2 is day 9, times 2 is day 10. So this is how many cents? 1,024 cents, which is $10.24, right? Don't forget, you get that all those old cents too. So now let's think about, what are we doing? We're raising 2 to the day power, right? So 2 to the 30th power gives us how much we'll get paid on day 30 of work. Wow. Can you see that? Let's write it out. You see that? Okay. Let's write out this number. All right. So now I'm going to do it in dollars and cents. So there's my $10,737,418.24 by day 30. Yeah, I think we'd work that. So what we're going to do here is we're just going to show this, and then we're going to create that equation. And now again, look at what I did here. I raised my base of 2 because I knew I was doubling each day to the 30th, which was how many days later am I looking at this, right? So let's kind of get this on the graph in a realistic sense. And then let's think about a function where pay is P and the function of days is D. So your pay, so P of D equals your base raised to your number of days. So there's your function figuring each of these out. Now, again, these are in cents, right? So I had to make sure I had this correct when I was converting into dollars and cents, okay? Use that exponential model to predict the pay if Jack were to work 20 days, right? Okay. Well, let's do P of 20 equals 2 to the 20th power. And let's see, it's going to be a little less than 10 million. So what's the pay? Oh, well, it's only $10,000, right? So P of 20 days is going to be, let me just write down the digits, and then we'll get some decimal places in there. Hold on one sec, kiddos. Okay, so we put our decimal point right here. Oops, you can't see what I'm doing right there. There we go. put our decimal point right here for our cents. And then every 3 numbers after that decimal point, that's where we put a comma, and that indicates our, hundreds, thousands, millions, billions, trillions, all that good stuff. So it can read it a lot easier. $10,485.76 after 20 days. I'd say I worked 20 days. That works for me. I like that. Okay, well, what we're going to do now is do the thing that it told me to do from the get-go, which is put this on the graph, right? So let's get our days is our X, and our pay is our Y, and of course that's in cents. So time is always X, right? So down here, I'm actually going to skip around a little bit. So I'm putting a little hash mark at every other box, and the reason is because there is no chance I'm fitting, more than 6 days worth of stuff on here, even with this grid being what it is. So I can afford to spread out some space on my x-axis. Now my y-axis is a different story. Okay, and we'll label x-axis our number of days. That's our time that's passing. Our y-axis is going to be a different story. So we're never going to be able to fit all this. Let's just go by fours, right? 4, 8, 12, 16, 20. And then we'll do this pay in cents. All right, and we'll see how many days we can fit that way. So it's not dollars and cents. This is just in cents. So like this is 2 cents, 4 cents, 6 cents, 16 cents. Okay. Anyway, I'll keep going that route, and I can fit a few more things. So 24, 28, 32, 36, 40 cents. 44, 48, 52, 56, 60 cents. 64, 68, 72, 76, 80 cents. Oh, and then this way I can get up to 100. Okay, cool. 84, 88, 92, 96, 100 cents, or $1 is the top of this, right? And how many days does it take us to even get close to that, right? We know that already. So we know that it was 7 days got us to $1.29.28. All right, so after 1 day, we know we're up 2 cents. Well, since this is going by fours, that's going to be halfway. Okay, start at 0 days, 1 penny. Think of it that way, and then go from there. 2 goes up to 4 cents. 3 days goes up to 8 cents. That's right here, 8 cents. 4 days goes up to 16 cents. That's right here, because that's 12, then 16. And then 5 days goes all the way up to 24, 28, 32, right here. 32 cents. 5 days, my bad. Put my dot in slightly the wrong spot. And then 6 days gets all the way up to 64 cents. So that's right here. There we go. 7 days, too much. 128 cents. That's too much. Okay. Now, Jack isn't getting paid in between. So since Jack's not getting paid in between, I'm not going to connect this. This is a discrete graph versus a continuous graph. And I know we've talked about that prior to now, but that's something that we kind of are mentioning again. We mention it much more in chapter 13. But what this is an exponential growth function. This is an exponential growth function where as our x is increasing, because we always think about our x's from left to right in our domain, then our y's are also increasing. And exponential growth functions are extremely rapid increases like this. We've already seen that when we were graphing yesterday, as far as how these graphs, these y values get just so much bigger, so much quicker. Okay? Now, let's take a look at a decay model in a real life scenario. By the way, if you can find someone that will pay you 1 cent the first day and then double your pay every day, obviously you need to work there. Obviously. And then quit after 30 days. You'll have 10 million bucks in the bank. All right, decay. Each year, a local country club sponsors a tennis tournament. Play starts with 128 participants. So 128 participants on day 0, right? Round 0. And then because it's a tournament and it's tennis and it's single elimination, each round, half the people are gone till there's one champion. That's how a tournament works. So after round 1 or after round 0 of play, when everyone's playing for the first time, think about that. Divide that by 2. 128 divided by 2 is 64. So there's 64 games happening. At the end of those 64 games, 1 winner, 1 loser. Loser goes home. How many people are left to play again? Well, there's 64 left for the next round. Okay, 64 divided by 2. Oh, there's 32 games that will be played, right? 32 winners, 32 losers go home. After that, let's divide that by 2. I think you see where this is going, yes? Okay, divide that by 2. Oh, 16 games, 16 winners, 16 losers. Divide that by 2. Round 4, you got 8 people, 8 games, 8 winners. And then divide that by 2, you got 4 games, 4 winners. Divide that by 2 for the next round, you got 2 winners that play for the championship. So round 7 is just the end, and it's your champ. Okay? That's your champion of your tournament. So what we can do here is use time as in the rounds of play. So I will use the same kind of hash marks as I go. So every other box, just like I did before. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 rounds of play. So what round are we in the tournament, right? Okay, then Y then must be our number of players remaining. Number of players. Okay, and why don't we just kind of go by 4s again? Because we know, oh shoot, we know that that'll fit 100. We need to get 128. Ew. Yuck. All right, I guess I got to go by 8s then. So 8, 16, 24, 32, 40. Yuck. That's going to be tough toward the end. Okay, then 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 is 80. 1, 2, 3, 4, 5 is 120. And that means this is 128 right there. That's what I was trying to get to. So now I'll fill back in. 8, 16, 24, 32, and 40. 48, 56, 64, 72, and 80. 88, 96, 104, 112, 120, 128. That's how many players I start with at the beginning of the tournament, right? So, boom, right there. And I'm just making that extra big so you can see where I end up. That's 0 rounds of play. After 1 round of play, we have 64 people remaining. After 2 rounds of play, we have 32 players remaining. After 3 rounds of play, we have 16 players remaining. After 4, we have 8 players remaining. 5, we have 4 players remaining. 6, we have 2 players remaining. In 7, we have 1 player remaining. And so you can see we're trying to get closer and closer and closer to having 0 players. If I were to take half again, I would have half. And then if I took half again, I'd have a fourth. And then if I took half again, I'd have an eighth. Obviously, we're not doing that because we're talking about human beings right now. But still, you can see what I'm talking about is that we've got this innate asymptote that we're trying to get towards, but can't quite make it. So after 5 rounds of play, how many players? 4 players remain. State your y-intercept value. And it's 128, and that's how many people start the tournament. How many people start at the beginning of the tournament? Let's write a function. And we're talking about P as in players, R as in rounds. So P of R equals 1/2 raised to the R power number of rounds. Does that make sense? Oh, I was going to say, it won't quite work. So let me try this instead. What's my initial value? How many people started? 128? So why don't I have that times 1/2 to the R power? Because if I plug that in right here, 128 times 1/2 to the, and we'll start with the 0 power right here. Right? And then I'll do second and enter and go back and change my exponent to be a 1. Now I've got 60. That's how it, so that initial value, my y-intercept, that means something, right? So you can see that meaning something as far as that's where we're going to start from, and then we're going to take half. That initial value will be part of our equation. What was that initial value on our first one? It was 1, right? It was 1 cent. Well, that means that makes more sense now. Okay. Because we're decreasing, this is a decay. We're getting smaller and smaller and smaller. As X increases, my number of people, my value, my Y value decreases. That's an exponential decay function. So let's put this together into one kind of growth and decay equation we can use. And that would be right here. I'm going to call it, when I write it out, because there's a couple of things on my piece of paper that did not go very well, but I'm going to call it y equals a, your initial value, times 1 plus or minus r, your rate of change, raised to the x, or t, because that's the time that this thing is happening over. And this is the general thing. I'll use the plus, I'll add 1 to my rate of change if I have a growth function. And I'll use the minus if I have a decay function. I'll do 1 minus the rate of change that way. So when you're thinking about the number in the parentheses, that number will be bigger than 1 for a growth function. It'll be smaller than 1 for a decay function. Let's think about this. Okay, so how this will work in practice, we'll look at questions like these two, where we'll write out the formula, and from the problem, we'll pick out what is the initial value, what is the increase or decrease rate, and then how long are we trying to do this over, okay? So that's what we're going to be doing in these questions. So we'll start with the original value of a painting is $9,000. The value increases 7% each year, right? An exponential growth function to model the situation and find the painting's value in 15 years. So first we need the function that does the general increase. And then we'll do it to a specific amount. Okay, so we need both of those things. So the first thing we need to decide as we're writing this formula is this going to be a plus sign or a minus sign? Are we growth or are we decay? And of course, if you read anything about a value increasing, then we're talking about growth. So it'll be A times 1 plus the rate raised to the x power. So now let's determine the initial value, A. It says substitute blank for A and blank for R. Okay. Substitute, find the initial value, which the original value of the painting is $9,000. So substitute 9,000 in for A. And the value increases at 7% each year. Well, the only problem with a percent, I'm not just going to straight write 7%. I need to turn that into the decimal form. So 7% is really 0.07. So we're going to put 0.07 in for R. So now let's substitute those in. Y equals 9,000 times 1 plus 0.07 raised to the x power. You can leave it just like that. That's the function modeling the situation. The next piece is to actually use an x value of 15. Okay, so I'm going to show you two ways that we do this. And again, this says t, I used x. That will be an interchangeable thing, as we saw when we were doing those with parabolas in chapter 11, right? So let's look at two ways of doing this. The first way is to just take this formula and just put a 15 right here and type that into our graphing calculator and see what we get. Now remember, we're talking about a painting's value, so we need to make sure our final answer is in dollars and cents. So 9,000 times 1 plus 0.07, end parenthesis, and then caret to the 15th power. So this is 15 years later. This painting is worth $24,831.28. So that's what I will write down. $24,831.28. Notice that's where I stopped, even though there were more decimals back there. We'd round to the nearest cent. The other way that you can do this is by going to y equals and typing in the general function right here. So remember, this was part of our answer, is we needed to see the general function, and then we substituted in the amount of time that's passed. So 9,000 times 1 plus, let's head back here. I didn't mean to go down there. Plus 0.07, end parenthesis, caret, and then this is where we put an x. So we want this to be different depending on what year, because I'm going to press second and graph to see my table of points. Now we know since x is time, we need to start at 0 at the lowest x value. And notice that's the initial value, $9,000. Then each year, that painting increases in value. So after 10 years, now all of a sudden, if you arrow over to the y value, 17.7, right? Then we'll keep going down and look at 15 years, which, look at that, exactly the same decimal we got on the home page, which tells me that if I need to find multiple years of value from this painting, I want to be plugging this in once to my y equals. If I only need to use it once, then that's when I can just plug it straight into the home screen right here. The population of a town is decreasing at a rate of 3% per year. In the year 2000, there were 1,700 people. Write an exponential decay function to model the situation, then find the population in the year 2012. So that right there, I know it's going to be 12 for T, because from the year 2000 to the year 2012, 12 years pass. So that's the first thing that I took in. The next thing I need to decide is this growth or decay. The population of a town is decreasing. Okay, that's decay. That's a minus sign. So let's write the general function y equals a times 1 minus r in parentheses and raised to the x power. We want to write the formula, then substitute something for a and something for r. What's our initial value? In the year 2000, there were 1,700 people. That's A. R is whatever 3% is as a decimal. So 3% is, take the decimal, move it 2 spots this way, 0.03 as a decimal. That's always, you always put the real decimal in for rate, not the percent. The percent is a representation to the nearest hundredths, right? 2 spaces behind to make it out of 100. Okay, that's what that percent really is. That's why it's percent per 100. So you know. So let's sub those in. Y equals 1,700 times 1 minus 0.03 raised to the x power. There's your general function. Now, I want to know about that in 12 years. What's the population of this town if we're losing 3% per year? And in 12 years, what's that population? Now, this is different because this will be to the nearest whole number, to the nearest person that we're rounding. So this is 1,700 times 1 minus 0.03, and then end parenthesis, and then exponent. So you want the caret button. 12 is 12 years from now, from the year 2000 to the year 2012. Ooh, wow, that's quite a lower population, right? Well, we're going to be rounding that up. So that would be 1,180 people in the town now. It's to the nearest whole number because we're talking about whole humans. Okay. So this is really what we want to take away. We kind of like generally spoke about growth and decay again, using some real life scenarios and graphs. But what we really want to take away today is the growth and decay function right here. That's what we're going to be using on our homework. A is that initial value, also the y-intercept. 1 is out of 100%. Are we adding to that or subtracting from that? And that's the rate here that needs to be a decimal. X is the amount of time that has passed. So that's the specific situation that you're talking about. Okay? All right, guys. Let me know how this goes. Good luck. We're doing another day, so we'll be looking at this again. I'll be seeing you soon.